In this chapter, we are going to talk about the logic gates. First, what are these logic gates? A logic gate is a basic component in any digital system. A logic gate is an electronic circuit having one or more inputs and only one output. And there is a relationship between input and output. This relationship based on a certain logic. So, according to this logic, the logic gates are named, and there are three basic logic gates which are AND, OR and NOT. And there are some logic gates that derived from these three basic logic gates, and they are NAND, NOR, XOR, XNOR. So these are the different types of logic gates. Now let's talk about these different types in next chapters. As the first gate, we are talking about the AND gate. AND gate is represented by this symbol. It has two inputs which are A and B and has one output. And this is the truth table for AND gate. When the input A is 0 and input B is 0, the output will be 0. And when the A is 0, B is 1, also the output will be 0. And when A is 1 and B is 0, the output will be 0. When A is 1 and B is 1, then the output will be 1. So, this AND gate produces a high output when only both inputs or all the inputs are high. This AND is represented by a dot. So, let's see how we can demonstrate this AND gate in our simulator. We are now in our simulator. So there is the truth table for this AND gate which I defined in here earlier. So let's see how we can get the AND gate in this simulator. First we have to go into this basic gates, and down here we can see in the first row there are AND gates. The first AND gate has two inputs, and the second AND gate has three inputs, and the third AND gate has four inputs. Let's take the first one, and as there are two inputs, we have to define two inputs. We get the first input like this, and I am going to name it as A, because in the truth table the first input is named as A. So here is A, and we can get another input, I am going to reduce the text height, and I am going to copy this A and paste it here and rename it to B. So there are two inputs, and this AND gate has one output. So we are going to get an output. We can place it here like this, parallel to the gate, and we can name it. I earlier copied this name, so I can place it here and this rename it as Q, which is the output name. So now we are going to connect this input to gate and this gate to this output. First we connect A and then we connect B. So the output is connected to this Q. Okay, this is the AND gate. Then check each one of these cases in this truth table. The first case is A and B both are 0. The output will be 0 as it is in the truth table. The output is 0. And as the second case, A is 0 and B is 1 and the output must be 0. So let's check it. A is 0 and B is 1. We can see the output is 0. In the third case, A is 1 and B is 0. The output must be 0. So let's check it. A is 1 and B is 0. As expected, the output is 0. In the last case, both A and B are 1. So let's check it. Then both A and B are 1. The output must be 1. So let's check it. A and B are 1. We can see the output is 1. So this is the circuit of AND gate, and let's move to the next gate. Our next gate is OR gate, and this is the symbol that we use to represent OR gate, and this OR gate has two inputs which are A and B, and it has one output which is Q. And let's fill the truth table for this OR gate. When the input A is 0 and input B is 0, the output will be 0. And when the input A is 0, input B is 1, the output will be 1. When A is 1, B is 0, the output will be 1. When both input A and input B are 1, the output will be 1. In this OR gate, the output will be low when only all the inputs are low. And this OR gate is represented by this plus sign. And let's move to our simulator and check how this OR gate is built. Now we are in our simulator, and I already defined the truth table for OR gate in here. So let's find the OR gate in this simulator. It is in the basic gates, and in the second row we can see there are three types of OR gates. The first has 2 inputs and the second has 3 inputs and the third OR gate has 4 inputs. And let's take the first OR gate which has 2 inputs, and as this OR gate has 2 inputs, we must define these 2 inputs. So I get an input like this and place it here, and I am going to name it. I name it as A, and we have to get another input, so it is here, and I am going to name it as B. So I am going to copy this first name and paste it here and rename it to B. And this NOR gate has one output. So let's get this output and we can name it as Q. So to name it, I paste this name label in here and rename it as Q. So let's, these are the basic parts in our OR gate. So let's connect this input to this gate and this output of this gate into this output. So first we are connecting the A input and then the B input, and then we can connect this output to this output LED bulb. So this NOR gate is like this, and let's check each of these cases in our truth table. The first case is both A and B are 0, the output must be 0. So it is visible that both A and B are 0, the output is 0. In the second case, A is 0 and B is 1. The output must be 1. So as we see, the output is 1. In the third case, A is 1 and B is 0. So the output must be 1. Let's check it. A is 1 and B is 0. The output is 1. In the last case, both A and B are 1 and then the output must be 1. So let's check it. Both A and B are 1. The output is 1. So this is the circuit of the OR gate, and let's move to the next gate. Our next logic gate is NOT gate. This is the symbol that we use to represent NOT gate, and it has only one input and it has one output. So this is let's fill the truth table for this NOT gate. When the input is 0, the output will be 1. When the input is 1, the output will be 0. So this NOT gate converts the input to its inversion. So this NOT gate is considered as an inverter. So let's move to our simulator and see how the NOT gate is constructed. So now we are in our simulator and this is a truth table for this NOT gate, and let's find this NOT gate. The NOT gate is in the invert and connect section, and there are two NOT gates, and it is first one is a normal inverter. I earlier said that NOT gate is recognized as an inverter, and the second one is a small inverter. Let's take this first inverter. As this NOT gate has one input, we have to define it. I'm going to name it as input. And this NOT gate has one output, and let's name it as output. So let's connect this together. Input is connected to the OR gate and the result is connected to the output. So we can see at the very beginning we can see the first case in our truth table where the input is 0, the output is 1. So we can see it here, the input is 0, the output is 1. In the second case, input is 1, the output is 0. It's very simple. This is the circuit of NOT gate, and let's move to the next gate. Our next logic gate is NAND gate, and this is the symbol that we use to represent NAND gate. This NAND gate has two inputs and it is called as A and B, and it has one output. What is this NAND gate means? This NAND gate is not AND. It can be represented by the combination of AND gate and NOT gate. So this NAND gate will produce the inversion of AND operation. So let's fill the truth table for this NAND gate. In the first case, our input A will be 0 and B is 0. The AND operation of A and B is 0. So the output of NAND gate is 1. At second, A is 0, B is 1. The AND operation of A and B is 0. The output will be 1. In the third case, input A is 1, input B is 0, AND operation of A and B is 0, so the output will be 1. In the last case, input A is 1, input B is 1, the AND operation of input A and B is equals to 1, so the output will be 0. So let's move to our simulator and check how we can represent this NAND gate in our simulator. So we are in our simulator now, and I draw the truth table for the NAND gate in here. So let's build that NAND gate. It is in the basic gate section, and it is in here with the AND gate with the small round in front of the AND gate. And so the first NAND gate has two inputs and the second gate has 3 inputs, and the fourth gate and the third gate has 4 inputs. And let's take the NAND gate with 2 inputs. As this NAND gate has 2 inputs, we have to define them. So we take an input, we place it here, and we can name it. I am going to name it as A. So this is input A, and we have to define the other input. So I am going to name it, and this is input B. So this NAND gate has one output, so we are going to place it here, and we have to name it. We name it as Q. So let's connect these inputs and gates. First A is connected and B is connected, and there is the output. So at the very beginning we can see the first case of our truth table. Both A and B are 0, the output is 1. When the A is 0 and B is 1, let's check it, the output is 1 as expected. And when, as the third case, A is 1 and B is 0, the output is 1, and as the last case, A is 1 and B is 1, the output is 0. So this is the circuit of a NAND gate. Let's move to the next gate. The next gate that we are going to discuss is the NOR gate. This is the symbol that we use to represent NOR gate. This NOR gate maybe have 2 inputs or more than 2 inputs, and it has one output, and this NOR gate is equivalent to NOT OR, which means the combination of OR and NOT gate. So this NOR gate produces the inversion of OR operation. So let's fill out the truth table for this NOR gate. When the input A is 0, B is 0, the operation of A and B is equal to 0. So the output of the NOR gate will be 1, because the output is the inversion of OR operation. As the second case, we have input A as 0, input B as 1, and the operation of A and B is equal to 1, and the output will be 0. As the third case, we have input A as 1, input B as 1, and the B as 0, and the operation of A and B is equal to 1, so the output will be 0. As the last case, we have input A as 1, input B as 1, so the operation of A and B is equal to 1, so the output of NOR gate will be 0. So in a NOR gate, the output is high when only the all the inputs are low. So let's move to our simulator and let's check how we can construct this NOR gate in our simulator. So we are in our simulator now. I drew the truth table for NOR gate in here. So let's build this circuit. This NOR gate is in the basic gate section, and as the first NOR gate, it has 2 inputs, and this second gate has 3 inputs, and the third gate has 4 inputs. And let's take this 2 input NOR gate, and we can place it here. And as this NOR gate has 2 inputs, we have to define them. First we take the first input and we have to name it. So I am going to name it as A. So as it has another input, we have to define it also, and we have to name it. which this input is B. So this NOR gate has one output. We have to define it also, and I'm going to name it as the output as Q. So here are they. Now we have to connect those. So input A is connected to this NOR gate and input B is connected to this NOR gate, and there is the output. In the very beginning, for the first case in our truth table, both A and B are equals to 0 and the Q will be 1. And as the second case, we have A as 0 and B as 1, the output will be 0. As the third case, we have A as 1 and B as 0, also the output will be 0. And at the last case, we have A as 1 and B as 1, the output will be 0. So this is how we demonstrate our NOR gate in our simulator, and let's move to the next gate. Now we are going to talk about the XOR gate, which is also known as the exclusive of OR gate. So this is the symbol that we use to represent XOR gate, and this XOR gate has two inputs, which are A and B. And there can be more than two inputs for XOR gate, and the minimum number of inputs is 2. So this XOR gate has one output, and this is how we represent the XOR function in an operation. So let's move to our simulator and check how this XOR gate is built. So we are in our simulator now. Here is the truth table for the XOR gate, but I didn't complete it. I left the output to be completed when we are building the circuit. So this is the exact expression for a XOR gate, and the output is equal to A and B bar or A bar and B. So let's build the circuit for this equation. As there are two inputs, we have to take two inputs. So let's do it. And I am going to name this input. I name this input as A. And as there is another input, I am going to put it in here, and I am going to name also this input. I name it as B. So as in this equation there are inverse of both A and B, so I have to attach a NOT gate to this circuit. So I get one NOR gate like this and another NOR gate like this. So we can say there are two AND operations, so we are going to include AND gate also in this circuit. And another AND gate. So as the final operator there is O, and I am going to take another O gate, and here is the and finally there must be the output, and I am going to name it as Q. So these are the components in our XOR gate or this equation. So let's connect them. For the first NAND gate, the A is connected and also the B bar is connected. And the next AND gate, the A bar is connected. And let's connect this to AND gate, and the B is connected. Like this. And results of these two AND gates are connected to this OR gate. Like this, and this will be the final output. So, according to our truth table, let's check these cases. When the A and B both are equal to 0, it is this state. So, we can see the output is 0. So, let's write it here. Okay. And for the next case, the A is equal to 0 and B is 1. So we can see the output is 1. Output is 1. And for the third case, B is 0 and A is 1. So the output is 1. The output is 1. And for the last case, both A and B are equal to 1. So the output will be 0. So this is the truth table for this XOR gate, and this is the this is how we represent the XOR gate using AND gates, OR gates, and NOT gates. So there is a equivalent. There is a one symbol, as I mentioned earlier, for this circuit, and it is here. This is equivalent to this circuit. So let's demonstrate it also, and we must have input and another input, and an output. So let's check this also. When the both inputs are 0, the output will be 0. When the first output is 1, we can see when the first input is 1, we can see output is 1. So when the second input is 1, we can see the output is 1, and when the both inputs are equal to 1, the output will be 0. So this is equivalent to this circuit. So this is the XOR gate, and this is how we represent it.